Welcome back to Multigrid Methods. We're in chapter 7, about to finish, I hope, because we're on slide deck 3 of 3. So I feel good about that. Um, so what we want to talk about in this last part are some uh, variations on the theme that we talked about already in chapter 7. So what have we talked about in chapter 7 so far? So to recap, we're looking at this equation in some relatively simple domain because we're in one dimension, and we're looking at boundary conditions which are also fairly simple. So what I want to talk about are variations on this in this section or these next two sections. The first one is, what if we have a coefficient in front of this? Well, I should I should say it like this. This second derivative or minus the second derivative can be thought of as the divergence of a flux, minus the divergence of a flux maybe, where the the mobility of that flux or the diffusivity of that flux is a constant coefficient. But what if it's not? In that case, then we have something a little bit more general for our law, something which might look like this: A U prime all primed equals F. So this is what we call the variable diffusivity case. The boundary conditions are the same as before, but this coefficient in here, sometimes called the diffusion coefficient or the diffusivity, in this case, we're going to assume is not constant. Now, I'm going to change the notation of this from what I have here. Usually we use A, but A we like to reserve as our bilinear form. So let's call our diffusion coefficient D, okay, for diffusivity. Now, that's one variation that we're going to talk about, and that's in this section, the variable diffusivity case. And then this section, we're going to talk about the cell-centered method in 2 dimensions. So I'll talk about exactly what you need to get a nice or normal or standard multi-grid method working in these frameworks. And then we'll also say a little bit about how you would analyze these algorithms to prove that they converge. What would you have to have in place? Well, we actually know all the things that we have to have in place. Those are the smoothing property, a smoothing principle, an approximation property two, and then some sort of Galerkin condition. So we need to establish those things in this new context because it might be a little bit different from this base case. So let's talk about one-dimensional problem where we have variable diffusivity. So this is the problem that we're going to study in this section. The boundary conditions are the same, homogeneous Dirichlet, and then minus the first derivative of D, that's our diffusion constant or diffusivity constant, which has to satisfy some sort of condition like this, times the first derivative of U. So we're taking the derivative of this product. What we need for D is that it should be a C1 function over the open interval 0 to 1 and a continuous function over the closed interval 0 to 1. And if it's continuous over this closed interval, this sort of condition makes sense here, that we can put bounds, upper and lower bound on this. Remember, a continuous function always attains its minimum and maximum. It's a bounded function. So we're going to say that it's bounded below by something which is positive. This says we have a positive diffusion, positive diffusivity. This is an absolute must. Well, I would say it's not an absolute must. There are problems where you can get away with a diffusion constant that decays down to 0, and what that's called is a degenerate case. But that's not what we're going to work with here. We're going to assume that we're bounded well away from 0. We're bounded above by some d max, so this thing can't blow up to infinity. We're going to operate in the framework of classical solutions for this problem to start with, and then we might later want to switch to weak solutions as usual if we want to do a finite element method or some sort of modified cell-centered method. And so that means we were looking for a U which satisfies this problem in this function space. And it satisfies this problem point-wise. It has to be globally C2 on the open interval 0, 1, and then continuous on the closed interval 0 to 1. So that's the variable diffusion problem or variable diffusivity coefficient case. We're looking for solutions that are in this function space which satisfies this problem point-wise. The thing we want to do now is come up with a finite difference approximation of this problem. So here's the way we're going to do this. Since the diffusion constant or coefficient is no longer constant, what we're going to do is think about what's going on here. We're taking the derivative of a product of things. The diffusion constant, I keep calling it a constant, but it's actually a coefficient. Diffusion coefficient times this derivative. So what I'm going to do is I'm going to think about what would happen if this is just a plain old function. Well, I would just use a cell-centered finite difference or center difference method to approximate this guy or approximate the derivative of this, right? So that would just be this minus that over HL, all right? So it would be the first finite difference. But actually, the thing that I'm taking a finite difference of can be itself broken up into something times a finite difference. So that's how we're going to treat this. It's going to be a finite difference of a product of something times another finite difference. And of course, when we do that, we're going to divide by HL twice because we're going to divide by HL here, and then we're going to divide by HL globally. All right, so there's two HL divisions. That's what gives rise to the HL squared here. We're going to multiply this diffusion coefficient times the difference, and then subtract from that the diffusion coefficient times the difference. All right, so what this looks like on a grid is we're trying to approximate things at the point I, say. And remember, I here references a cell center. We have these points here, I plus, or sorry, would be I minus a half, and I plus a half. And then out here would be I plus 1. Nope, I'm counting backwards. I minus 1, right? And here, I plus 1. So what we're doing is when we calculate this finite difference here, we're doing I plus 1 minus I, okay? I plus 1 minus VI. That's giving me a difference if I think of the center difference context here. So what I'm going to do is I'm going to multiply the diffusion constant that's evaluated at I plus a half. That's going to be that value there. Okay, so that's how I define my diffusion constant evaluated at this half interval, okay? So in cell-centered context, the cell-centered points would be here, here, and here. And these guys here, maybe we'll call them blue points, are what we call edge-centered points. So the cell-centered points are at the red circles. The edge-centered points are the blue dashes. They're halfway between these cell-centered points. This is where I'm going to define my diffusion constants or diffusion coefficients. Okay, I'm going to define those at this point, and of course that keeps going, goes forward and backwards on the grid. But what we're really focused on is how are we going to calculate this finite difference approximation, the second difference at this point? Well, I need to take a finite difference here, and I'm going to take a finite difference here. We already talked about this one. What about this one? Well, this one is going to be another cell-centered finite difference approximation given to me here. So that's going to be VI minus VI minus 1. And that's going to land me at this point, meaning it's going to be an approximation at this point. So I'm going to multiply the diffusion coefficient at that point. The definition of that is just the whatever that function is, d, evaluated at this point. Okay, and that all of them are given by this formula, this generic formula. So that's the idea of this finite difference. I'm taking two finite differences. I'm taking first this guy and that one, and then I'm taking the difference of those two. But now I have to account for the fact that there's one big minus sign out in front of everything. So I get minus a finite difference at the end. So that's why I've changed the sign from plus here to a minus, and this minus gets changed to a plus. Why am I dividing by two h's? That's because I've done exactly two finite differences. I've done one finite difference here and here, and then I've done a second global finite difference, which gives me my second power of h, all over h L squared. So this is our cell-centered approximation for this non-constant coefficient diffusion operator. All right, we're going to give it a name, and we're going to call it minus um, delta LD. This just means the second finite difference or the second degree difference. The reason why we're giving it delta and calling that the second degree difference is because that's fairly usual. We call something the Laplacian operator if it's two derivatives. We're going to use this superscript d to denote the fact that our diffusion constant coefficient is non-constant. Okay? Diffusion coefficient is non-constant, or at least not equal to the constant 1. And of course, we're acting on some grid function. So that's what all this notation means, and that's the derivation of this second finite difference operation whenever the diffusivity is not a constant. So this leads right away to a finite difference problem. The cell-centered finite difference problem in particular is we want to find a u that is a cell-centered function on level L. So we're just dealing with one grid, so we're going to call that generic grid the level L grid, such that that grid function is equal to 0 at the left and right boundaries at 0 and 1. And remember, that's a discrete homogeneous boundary condition, meaning what we do is we take the average and we force that the average is equal to 0 at 0 and 1. We're looking for such a function that satisfies this equation, okay, for all I between 1 and n L. Actually, this one doesn't have to be given with an index I. This index here is associated to the definition of this. What is this guy over here? We didn't define that yet. So this is defined as a cell-centered function, but only in the interior. That's what we mean by an interior, or that's the notation we use to designate an interior finite difference function. That means it doesn't have values at the ghost points because, in fact, we don't actually need their values of f at the ghost points. So this is defined for I between 1 and NL as FLI, that's the ith coordinate of this grid function. FLI is FXLI. That just means we're going to take the continuous function f and we're going to sample its values at the cell-centered grid points, and that gives us a function. So here's the idea. Whenever you have a function that is continuous over a grid, and then you want to fill up the grid values, well, you have the grid values being, let's say, here, here, and here at these 4 points. All you have to do is sample the value of the function at those 4 points. So we have the function values here, here, and here, right? So as long as it's a continuous function, it has point values, we can evaluate it at its point values and get a grid function from it, namely that. So this is our complete finite difference approximation for this new case where we have variable diffusivity or a variable non-constant diffusion coefficient. Now, I'm not proving that this is a second order scheme, but if you do Taylor expansions, you can show pretty straightforwardly that it is a second order scheme in time. That means that the local truncation error has a certain nice property. And I'll refer you to a good numerical analysis book, such as the one that Dr. Salgado and I wrote, to look up what we mean by second order there. So now we're going to the first thing we want to do is turn this finite difference problem into a matrix problem. And so what we can do is figure out how we can turn these equations into at least hopefully linear equations, and then peel off the coefficients and formulate some sort of coefficient matrix and show that it's a matrix vector problem. So that's the idea. So to obtain the first equation, we're going to set I equals 1 in equation 3. That's our finite difference approximation here. And so I equals 1, if we get the way I wrote it first time is I didn't gather terms together, but you'll notice that this term here and here, so we can combine those two terms together rather than having these two terms combined together. And I can use the distributive property to pull out coefficients. And so you'll see this term here could be rewritten, the center term, VLI. If I collect the two terms that are associated with that one, I'm going to have a plus and a minus diffusion constant. So it's going to be minus DLI plus a half and plus DLI minus a half, right? And of course, I can't forget I have to divide by HL squared. So I could combine this term and this term together into one term, which looks like that. So that's what I'm doing in this step here. I'm taking this for I equals 1, of course, and I'm combining those two central terms and leaving the two other terms by themselves. Now we have to use the boundary conditions in order to get rid of this guy here, because we don't want that to be a true degree of freedom. So how do we do that? Well, the boundary condition says, remember, it's a homogeneous, uh, it's a discrete homogeneous Dirichlet boundary condition that says that UL0 equals minus UL comma 1. And that's just expressing the fact that the average of the two values across the nearest to x equals 0 equals 0. The average equals 0. And so that tells me that the value at the go cell is equal to minus the value at the first uh, degree of freedom. So if I substitute this, or I should say this value in for this value here, then that means that this value is gone, and I can combine what results with this term. If I do that, then what changes is instead of getting this coefficient in front of this value, I get this new coefficient. Okay, the HL squared just goes along for the ride. I can do this manipulation entirely inside these two square brackets. So my coefficient on UL1 becomes this, and there's a coefficient which is going to appear on when I start collecting things in the coefficient matrix, which multiplies UL2. All right. So now let's go on. Let's what about the second equation? That is whenever I set I equals 2 in 3. Well, between 2 and NL minus 1, the equation is exactly just 3, okay? So I can just use this equation without applying any boundary conditions. So all I do is apply this guy, this definition, and I combine the two middle terms together. So that's all I do for those equations. So I just use 3 and I combine the terms in the right way. All right, using the right boundary condition, I can address the last equation. So the last equation is the one where I is equal to NL minus 1. So I should probably have said that. So for the last equation, I is equal to NL, not minus 1, but just NL. So I is equal to NL. So you'll see that what I get is, in the end, something analogous to what I got with whenever I was equal to 1. I'm going to get a middle term multiplying UL NL, and a term also that multiplies UL NL plus 1, but I can eliminate that guy using the boundary condition. That changes the value of the coefficient multiplying that, because I'm going to eliminate this in favor of that. So that means that this is my last equation. That tells me how I can pick off these coefficients and build a coefficient matrix. So you can see pretty easily, at least I hope, that the level L stiffness matrix, which is what I'm going to call my coefficient matrix, is going to be tridiagonal. So here's um, here's kind of evidence of it. For the first equations, I'm going to have two coefficients um, for my coefficient matrix, and all the other coefficients are going to be zero. See, because there's no UL3 term. Okay, so I can just assume that the coefficient is equal to zero in that case. Okay, so these are essentially zero out here. All right, or I could just assume that it's just one giant zero. Okay, but now what are these coefficients on the diagonal? The only ones that I've computed really are these two guys here and these two guys here. So the first coefficient is this guy here. Okay. The second coefficient in the first row is going to be that guy. So minus b is going to come there, minus b1. But what about this guy? We've calculated that coefficient as well. That's this guy. And we've calculated this coefficient, which follows this formula. So those are the only coefficients that we actually know. Anyway, so this is the coefficient matrix that we get. Okay. Um, the coefficient, or sorry, the unknowns are going to be gathered together in a vector called U sub L. And the forcing vector, the forcing term, the right-hand side vector is just going to be F, and that is just what you would expect it to be. It's just the coefficients, the entries, I'm sorry, of this grid function F. Okay, so that's how we formulate this matrix vector problem. All right, so now that so I already gave one operator, one version of this operator, and that acts on functions like we said that have this homogeneous Dirichlet boundary conditions built into them. However, we could think about this operator as being slightly redefined so that we build the boundary conditions into the operator. And whenever we think about the boundary conditions being built into the definition of the operator, what we're going to do in that case is we're just going to add this extra little circ symbol. Okay, this I don't in LaTeX it's called a circ symbol. We can call it a zero or whatever. It's kind of an interior symbol as well. So this just means the operator with the boundary conditions built directly into the operator. Okay, so we'll distinguish between this guy, which acts on these functions, uh, which actually have degrees of freedom at the ghost cells, but they're eliminated because of the homogeneous Dirichlet boundary condition. And this operator here, which only acts on interior functions, cell-centered functions that are only defined on the interior. Okay. So, and the reason that can act on those functions is because the boundary conditions are already built directly into the operator. All right, so the first thing I want to do, here's a typo that I want to address. We want to prove that the wrap condition holds for this case. Well, because we've defined these coefficient matrices, these stiffness matrices on all levels, we can ask the question, does the Galerkin condition hold? I shouldn't have called it the wrap condition. It's because it's not the standard Galerkin condition, right? It's an imbalanced Galerkin condition. The reason we call it an imbalanced Galerkin condition is because this wrap condition holds except for the fact that there's a 2 over here. It holds as usual, but with a 2. All right, so that's what we call the imbalanced Galerkin condition. How can we prove that this holds? So let's see, actually go through the calculation somewhat. So we're going to prove that this imbalanced Galerkin condition holds. So how can we do that? Um, so to simplify some of the arguments, I need to introduce some notation that is going to make life simple for us. All right, so let's set, let's let V, we're going to act on both of these guys with vectors, and we're going to let VL be that vector. So let that be arbitrary, VL minus 1. So that's, of course, a vector in RNL minus 1. And we're going to define VL to be the prolongation of that. All right, so this can then be related to some grid function in this interior grid function space, CL minus 1, 0, or circ, I guess, through this grid function basis. This, uh, this vector is related to some grid function VL through the basis on level L. And of course, this grid function lives in CL circ. This means cell-centered grid function that has only interior values. It doesn't have anything in the exterior. It doesn't have any ghost cells. All right, now let's let the index on level L minus 1 grid be the symbol capital I. It's a little bit hard to see that that's a capital I, but kind of looks like an L. It's going to be a capital I. And so this index runs from between 1 and NL minus 1. The index on the level L grid is going to be the symbol little I, and that is going to go between 1 and NL. Okay, so I'll show you the figure on the next slide. They line up exactly at one spot, or they kind of line up. So here is where I'm going to show you the indexing for the fine level grid. And here's the indexing for my coarse level grid. Okay, so the coarse level grid, cell center grid, just has these 3 points. And the fine level grid has these 6 points, 1, 2, 3, 4, 5, 6. Okay. Now, like I said, it just so happens that they kind of line up so that this point here is labeled I. This is I plus 1, I plus 2, and so on, little I. This is I on the coarse grid, but it's labeled with capital I. Capital I plus 1, capital I minus 1, etc. Now, remember, whenever the cell-centered grid point and well, let's see, the coarse level cell-centered grid and the fine level cell-centered grid have 2 different interpretations of what an edge point looks like. So, or a vertex point, in other words. So with respect to the coarse level, which is this guy, this point here is an edge point, and this point here is an edge point, and so on and so forth. So this point here gets labeled capital I minus a half. This point here, I plus a half. Now let's go to the fine level grid. So fine level grid, it has a lot more indices, so I've kind of staggered things here. So I refers to this point, I plus 1, I plus 2, and so on. But its edge-centered points are here, 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 and here, right? And it goes this way as well. So the edge-centered points don't exactly line up always, but they do at a couple of points. So the edge center point for the fine and coarse level grids line up at this point, and of course these points as well. All right, so this is how my nomenclature is going to go, my indexing is going to go. All right, does everybody get that? Cell center point for the coarse level grid, cell center point for the fine level grid, edge center points for the coarse level grid, edge center points for the fine level grid. Okay, but I don't need indices on everything, only for a few things on what I'm about to do. All right, now I want to show that this imbalanced Galerkin condition holds. And so what I want to do is act on this. I want to take this operator and act on an arbitrary vector, and take this and act on an arbitrary vector, show that I get the same things. Well, These operations here can be related to operations on grid functions, as can this guy can be related to operations on grid functions. So that's what I'm going to try to do. Let's look at what does this operation on this vector look like if I translate that into the grid function setting. So I'm going to look at the application of this matrix to this vector at this point or this index capital I. And I'm going to call that T. So now that means I want to show that that is exactly equal to 2AL minus 1, BL minus 1, I. I want to show that those two things are equal. But now the way I'm going to do this is just to realize that these operations can be translated into operations on grid functions. So how can I do that? So let's look at this, what's going on here. You can think about this being a grid function, right? It's a vector, but it can also be just translated into grid function. We can turn its values into grid function points. So what I do first with that function is I prolongate it up to the fine level grid. Then I act on that with the the fine level grid operator, the fine level finite difference operator, and then I take the average of that and push it back down into the coarse grid. That's what a restriction operation is. It's just an averaging procedure, right? So that's what I'm doing. I'm taking a grid function, prolongating it to the fine level grid, applying the finite difference operator onto that, and then I'm going to restrict that grid function back down to the coarse grid but through averaging. All right, so that whole operation translates into these two steps right here. Okay, so if I apply, so I'm going to think about, remember, I'm going to call this guy my fine level grid function through this assumption here, right? So when I prolongate up to the fine level grid, I get a fine level grid function, which is defined by this vector. So this is just my finite difference operator acting on that vector in two ways, okay? The reason why I'm doing two is because I'm going to have to take an average of those two values. So now just block that guy out. This is the finite difference operator acting on a grid function, and then this is taking the average of that guy. So here's that average being done. Well, this is the finite difference operator acting on the grid function. And this, the fact that there's two of these with a half, that's the average. Okay? So the first job is prolongate, apply the operator, take the restriction to average back down um, to the course level grid. So that's what's encapsulated here. Now, let's think about how this prolongation operation works. It's going to push some vector up into the fine level grid, but how does it do that? Well, this value is what gets pushed up into the fine level grid as that value. Let's go back and confirm that. VLI gets pushed up into VLI plus 1. So VLI, that's that value. So remember that value, whenever on the coarse level grid, gets pushed up into two values. One is going to be defined here, and one is going to be defined here. So it's going to give its values. So think about how the prolongation operator works. So if I have a grid function, and it's defined here and here, when I prolongate it, it turns into the grid function with 4 degrees of freedom. One of them disappeared. Okay. So this two value breaks up into two values, and this value breaks into two values. So it's this value here, which is going to that value, and this value here is going to that value. And likewise, this value goes into two values. And this value here goes into two values. Okay. Now, these aren't the values that it's taking. It's just the location of where I'm sampling those functions. So you can see this is this value here is what gave rise to that value. So we could just change this value back down to that value. And this one as well. This is the value at the fine level grid at index little I. Well, that comes from this guy from the coarse level grid. Okay, the grid function at level L minus one at the index capital I. Same with this one. VLI, where does that come from? VLI minus one, I, capital I. This guy, where does that come from? That's VLI minus one. VLI minus one, that's the value there. Well, it comes from this guy here, right? So this guy here gets replaced with that value. So we do that for all 8 of these values. So 1, 2, but some of them are repeated, of course, and so we don't have to do it for all 8. By the way, there is some savings that I could have done here to make life a lot simpler for myself, because I could have noticed right away that I could have just gotten a cancellation of these two terms, right? These two terms, no matter how you cut it, are exactly the same. So I could have deleted those at the beginning. And the only thing that would have been left is these two terms which survive. You can still see that here and here, right? These two terms are exactly the same. And so they're going to delete each other. They're going to combine and annihilate each other no matter how things work out. It's only these two terms which are going to survive. All right. So to recap, I'm prolongating a vector from the coarse level grid up to a fine level grid. I'm acting with the fine level operator, the finite difference operator. Then I'm taking the average and pushing that back down to the coarse grid. And that's encompassed in these two steps here. And that's translated into this guy. And no matter how you cut it, these two terms are going to annihilate each other. So the only thing that's going to survive, because I've canceled these two, these are called flux terms, by the way. Those two flux terms annihilate each other. And the only two flux terms that survive are this one and that. Oh, no, is that right? Which one's canceled? It's these two that cancel. So the second and third terms survive. Okay, so I'm going to write this guy and that guy. All right. And now the next step, the only thing I'm doing is converting that HL into 1/2 HL minus 1. Okay, HL is just 1/2 HL minus 1, so I'm converting that. And the reason I want to do that is because I want to try to, remember I said I want to try to show that this guy is equal to that. This involves the finite difference operator at the coarse level. And so I want to try to convert everything into something which looks like that. So that's where I'm going, trying to convert everything into something which looks like the operator at the coarse level. All right, so everything's looking good now because this here is looking like the finite difference operator at the coarse level. So the only thing that's missing is this is the finite, or this is the diffusion constant at the fine level grid. And this is the diffusion constant at the fine level grid. But notice that this point here, Li plus 3/2 is exactly the same point on the coarse grid with the index I plus 1/2, only I'm missing my 1 here. So that's a typo. So there should be a 1 there. Okay. Uh, how do I know that? Well, I just said that, for example, these 2 points, right? That's fine level grid, edge grid point with the index little I plus 3/2. And this one is the coarse level grid point with index I plus 1/2. Those are the same. And these two are the same. So this one is the same. This one is the same. They just have different notation. But now once you see I've gotten to this point, well, notice by the way, where did the half go? Well, I have a half. Remember, HL is equal to half HL minus 1. So I take this half and I square it, I get a quarter. So that becomes 4 times a half. I get a 4 out front, which becomes a 2. What's left is HL minus 1. That's good because that's the grid spacing on the course level. And all this thing here is the course level finite difference operator. So remember, that's can be translated into a matrix vector multiplication. That's exactly AL minus 1 times VL minus 1 evaluated at the grid point capital I. So I've just shown that exactly what I wanted to show. This is equal to that. But that shows that I have exactly what I want. This imbalance Galerkin condition, this imbalance wrap condition holds. So assumption G3 holds for my problem. So this shows that if I do a careful distribution or definition of points, that my finite difference operator or my multigrid works out to have satisfied the imbalance Galerkin condition. All right, now there are two missing pieces to finish off this variable diffusivity case for the one-dimensional case. So we've shown that assumption G3 holds, but what missing pieces are there? You need to show the smoothing property holds or smoothing principle holds using maybe a Richardson type smoother, but that's not easy anymore because we know that those sign modes that are usually the eigenfunctions for the stiffness matrix are not necessarily the eigenvectors for the stiffness matrix anymore. Something more complicated is happening since we have a variable diffusivity. So we've got to use a different type of analysis to analyze what's happening with the Richardson type smoother. So that's a missing piece. The other missing piece is the approximation property doesn't necessarily hold. So what do we do? Well, we can't answer without filling in those details whether or not our multigrid method converges or not. We simply don't know. Um, I don't know the full answer to the questions is how or what you need to do in order to get this to work. All I know is that there has been some work done on this, and we're not going to address this here because it's way beyond what we want to deal with in this course. So I'm going to just say there are two missing pieces that can be filled in, and you can pursue that if you're interested. All right, so we're going to start off this next section with a big typo. This should not read variable diffusion case or diffusivity case. It should say cell-centered multigrid in 2D. In other words, it should be the same section title as that. So that's a typo. So that's where we're going now, cell-centered multigrid in 2 dimensions. I'm going to start the problem off in just a completely general setting. So this is the problem that I want to define or explain, and then we're going to figure out how to solve that. So in 2 dimensions, we're going to solve minus the divergence of d times nabla u. D is our diffusion coefficient. And so this is a scalar times a vector, right? So scalar times a vector is going to give us a vector, and then we take the divergence of that. The diffusion or coefficient or diffusivity satisfies something similar to what it did before. It has to be bounded below, well away from 0, and bounded above. Okay, but otherwise we're going to seek a classical solution for this problem. And the approximation can be carried out in the cell-centered finite difference case the same way it was before, but we have to define what we mean by cell-centered finite differencing in 2 dimensions. So I'm going to start off by saying, let's let the I think I said it here, but failed to mention that we're going to be doing our approximation on the unit square because that's the simplest thing to do. And we're just going to make a standard finite difference type grid for that square mesh. All right. And here are the locations of the cell center points in this case. We're going to assume that the number of grid points going in this direction is going to be ML, and the number of grid points in this direction is ML. All right. And so the mesh spacing in both dimensions, what we're going to call HL, is just going to be 1 over ML. How are we going to define this, the value of ML in this direction and this direction, the number of points? We're just going to set that to be Q times 2 to the L power, where Q is just some positive integer. All right, so here's what a typical grid looks like in 2D. And this is the case for L equals 2 and L equals 3. Let's see, I guess whenever Q is equal to 1, probably should have said that. Q equals 1, right? So if Q is equal to 1 and L is equal to 2, then that's ML is just going to be 1 times 2 to the 2, so 4. Yeah, that works out. And if we go to the next level, we're just going to double the number of grid points. And so what we're trying to do is characterize the locations of these blue points. Those are the cell-centered points. So cell-centered points in 2 dimensions are a little bit different than 1 dimension because, um, well, uh, I guess it's kind of obvious why. So the cell-centered grid points are defined by the following tuple of points. So we're going to say that the vector point xlij is equal to zeta li, zeta lj, where zeta lk per any k is equal to k minus a half times hl. So this is the same as the definition we had in one space dimension. Now the set of cell-centered grid points is going to be those sets of blue points that we have here, plus these points that you see out here, this collection of open circles. Those are called the ghost cells. And notice that there's no ghost cells here, here, and here, and here. Those 4 points don't have ghost cells associated to them. And the reason why is kind of complicated, so I'm not going to go into it in any depth, but just suffice it to say, we don't need ghost cells at those points. And so I'm going to define the set of cell-centered grid points as a set of all points which satisfy this definition for j and I between 0 and ml plus 1. That would grab all the points that would grab simply all of the points. But I'm going to delete these 4. I'm going to go back and delete these 4 because I don't need them. So that's why I'm subtracting off of those 4 particular points. And the reason is it might not be entirely clear, but I just won't need them. The grid points that don't belong to this original set omega are called ghost points. So those are the open circles here, the non-filled circles, unfilled, I guess. And the set of interior grid cell center grid points, it's all the blue points. Okay, anything in here. If I take the set of cell center grid points and I intersect them with omega, then I just simply get all of the interior cell center grid points. Now the grid cells themselves are these sets. Okay, that's what we call a grid cell. And so that's why we call it the cell center method, because we're looking at points that are evaluated at the center of the cell. And I'm going to define the grid cells in an analogous way to what I did in 1 dimension. I'm going to define them as half open. But in this case, because it's 2-dimensional, I'm going to do the cross product of 2 half open intervals. And I'm going to call those grid cells K, L, I, and J. Now I'm going to define something called the space of piecewise constant function as before. The space of piecewise constant functions in this case, let me see if I can be slightly artistic here. Probably going to fail, but I can try. So I have a grid, and let's say we have this very simple grid with two cells in one direction and two cells in the next direction. So a piecewise constant function would be a function which is constant on those grid cells. So for example, one of them might look like this. There's one piecewise constant value. Let's make the next one green so that it doesn't interfere. Purple guy here. Let's do orange next. Orange might be up here. And finally blue maybe. Okay, so that's what a piecewise constant function looks like. Maybe one of you artistic fellows uh, could uh, could could knock up a LaTeX drawing or a TIX drawing of that. All right, so that's what a piecewise constant function looks like. The way we define it is fairly simple, right? So it's easier to define than it is to draw. It's any function defined on this half open square into or with values in the real numbers, such that when I restrict them to any one of those cells, like these objects here, it's a piecewise constant function or a polynomial of degree 0, which is a constant function. Okay, so each restriction of the function to each cell is a constant function for each cell in the grid. The space of cell-centered grid functions and interior cell-centered grid functions are defined respectively like this. So the only difference here is I'm introducing this kind of script. So this is my set of cell-centered points, and the space of functions defined on those cell-centered points is defined similarly, but with a script C. So they're functions V which take these cell-centered grid points and map them into R. And the interior cell-centered grid functions are those that take the interior cell-centered grid points and map those to R. So each cell-centered grid point gets a point in the real line. The subspace of homogeneous Dirichlet cell-centered grid functions is denoted this way. Okay, it's a set of all cell-centered grid functions that are 0 on the boundary. And what do we mean by 0 on the boundary? 0 on the boundary means that the averages across the boundary points are all equal to 0. So for example, if this is my mesh, and I have a cell center point here, and this is the boundary, then I have a grid or a ghost cell here, right? So what we're saying is the values at these 2 points, if I take the average is naturally going to be located here and here. All right, so the values of the average should be exactly equal to 0. That's a good way of mimicking what's going on with the homogeneous or with the Dirichlet boundary conditions. Okay, now why don't I need, so this is a good place to address why I don't really need a ghost cell in the corners. So if let's use blue some more here. And suppose our physical boundary is denoted by the black line. So if if I'm looking at the point 0, 0, then I have the crossing of 2 physical boundaries. Then I need to take the average, of course, as I did here and here and here and here. The next average I'm going to take is this guy and this guy, and the values of the average are going to be located at these points, right? And the point is, I don't need to take an average this way. I don't need to define the average value there. So I don't need that cell-centered grid points. I only need the ones going along here, going along here. I don't need the one in that corner. But that's all that's happening with these averages. So this represents the average, what, across this boundary here. So that goes from J equals 1 up to ML. So that's going that way. This is going to be the average here along this boundary, right? So for any I and J between J equals 0 and 1. So 0 is this go cell and 1 is that go cell. 0 and 1. So I want their averages this way to be equal to 0. So that's exactly what I'm representing there. Now I can just multiply both sides by that 2, and I can get rid of the 2, right? So the 2 is just um, is completely unnecessary. But I like to think about this as being the average is equal to 0. Once I get rid of the 2, I could then, let's say for this guy, I can move this one to the other side, right? And so that I get UL0J is equal to UL1J with a minus sign, right? So that's how I build up my boundary conditions. Okay, so I'm just going to use this as shorthand notation to mean that that happens. So if I use VL is equal to 0 on partial omega, then V is going to replace U in these four equations. So this is what I call the discrete homogeneous Dirichlet boundary conditions. Now, as in the one-dimensional case, there's a canonical way to relate functions that are in these three different spaces. This is the space of cell-centered functions, or sorry, of piecewise constant functions, cell-centered functions that are homogeneous Dirichlet on the boundary, defined here. Remember, this is my restriction on this set of functions. They have to have this discrete homogeneous boundary conditions holding. So that's that function space there. That can be related to these functions, can be related to these, and this can be related as well. These are the space of cell-centered functions defined only on the interior grid points, and I defined that here. So those are functions that are only defined on the interior grid points. I can, okay, so all of these can be related to each other, these function spaces. They can be put into correspondence with each other. That's probably a better way of saying it. They can be put into correspondence. Okay, put into correspondence with each other. All right, I'm not going to show you exactly how to do that. I'm just going to argue that it can be done. But they can all, in turn, be put into correspondence with vectors from this vector space, R with dimension ML squared. It kind of makes sense, I hope, because I can think about, let's take the very simple grid that has two grid points, two grid cells going in each direction. So if ML is equal to 2, so ML in this case is equal to 2, then the total number of degrees of freedom here is 1, 2, 3, 4. It's ML squared. So I can think about turning grid functions that are defined only on the interior grid points into vectors with a length that is equal to ML squared. Or in other words, you take the number of, to find out the number of degrees of freedom, you just take the number of grid points in any direction and you square it. So ML gets squared, and I can translate grid functions into vectors which look like that. So it's pretty easy to see how you do this translation, but there are a number of ways I could do it in practice. I could count this way. I could say 1, 2, 3, 4. or I could do 1, 2, 3, 4. So I could do this correspondence in any way I want. Here's how I'm going to do it. I'm going to say that a grid function gets turned into a vector according to this correspondence. This is called the lexicographic correspondence. This is kind of complicated looking, but it's actually quite simple. It just means you're going to count like a typewriter, but you're going from the lower left-hand corner to the upper right. So you count in rows like this. 1, 2, 3. So let's do an example where I have ml equals 4. So for ml equals 4, we have this case. So we know we're going to have 16 degrees of freedom. But how do we count those degrees of freedom? How do we turn those into a vector? Well, I'm going to do it in this way. I'm going to count this way. 1, 2, 3, 4. I'm going to stop at 4, go up here to count, continue counting 5. 5, 6, 7, 8. Stop there. Continue up here to count 9, 10, 11, 12, 13, 14, 15, 16. All right, so that's what this notation means. Basically, I'm going to count rows first, and then I'm going to count columns. That's what that means. So this identification, in any case, shows that the dimension of this function space is exactly ml squared. But if all of these can be put into correspondence with this guy, then that shows the dimension of each one of these spaces is exactly that. So when I translate these grid functions into these vectors, that's called the lexicographic or the canonical lexicographic correspondence. Okay, it's the normal way you would count. It's a little bit like you're counting X first and then Y second. Okay. Now, to keep our notation consistent and standardized from what we've had all along, we're just going to say that the total number of degrees of freedom from our function space is equal to NL. But NL, that's the total number of degrees of freedom, is related to the number of grid points we have in this direction as follows. It's just equal to ML squared. You take ML in this direction, ML in that direction, they just so happen to be the same, so you just square it. All right. Um, and I've already said this. All the dimension of all those spaces is equal to ML squared, which is equal to what I'm going to call now NL. Now let's first go over the case of constant diffusivity and then go into non-constant diffusivity. So what is the constant diffusivity case look like? Well, for the constant diffusivity case, the I've got to approximate this operator. But if this operator, or sorry, if d is equal to 1, then this operator is just the minus Laplacian operator. So the approximation of that is fairly standard. You've all seen the 5-point approximation of that. And it can be thought of in this way, and it can be kind of derived pretty simply. So this guy is just equal to the minus Laplacian operator. We know that. But what is this? This is just the second derivative in x and the second derivative in y. Okay. So really all I have to do is take the 3-point stencil involving u here, and then I turn it, go the other way, 3-point stencil for u in terms of y. Okay, so I should have said the 3-point stencil, but going in the x direction, the 3-point stencil going in the y direction. And that gives us just our usual 5-point stencil if we want to think about things in a fairly mechanical terms, right? That gives us a 5-point stencil. The big difference between what we have in 1D and 2D is that the element in the middle gets numbered or gets the index or the coefficient +4, okay, instead of +2. This operator here, you may have seen it represented as stencil before. And so basically the way a stencil works is you think about a grid function, right? So our typical grid function might look like this. or it's not going to look like this, but it's going to have values at these grid points. Remember, the grid function itself now is a kind of two-dimensional object, right? Because um, it let me try to be artistic here once again, and hopefully not fail too badly at that. So, right, so there's our cell-centered grid points, all 16 of them. And of course, what each one of those grid points has a value associated to it, right? Okay, and let's say this guy might be way up here. All right, so that's what a cell-centered grid function looks like. It has values defined at the grid points. But what is a stencil doing? Well, again, we want to look at the grid, not the grid functions, right? So here's a grid what has 16 points in it. Suppose we want to calculate this operator on a grid function at that point. Well, we're going to apply the 5-point stencil to do that, right? So we're going to take the value there and we're going to multiply it by 4. We're going to take the value at this point, multiply it by -1. Same here and same here, multiply by -1. Add all those up and then divide by HL squared. And that's what this stencil represents. And that's why it's in that shape. It's telling you what coefficients you should use when you um, when you multiply the various values of the grid function. And that should be understood that it's completely encoded in here. The only difference is this has to change a little bit when you get near a boundary, because when I go across a boundary, I might have to apply the stencil at these 4 points, right? So I need to know what is the boundary condition over there in order to apply it to the boundary. Or I could build the boundary condition into the definition of the operator, like I did in the one-dimensional case. But we're getting a little bit ahead of ourselves. We want to formulate our cell-centered finite difference problem for this 2D case where we have a constant diffusivity. And so that's where I'm going to pick up next time. I'm going to stop there. Um, and so the next thing we need to do is define how we sample F, and then we just set our homogeneous or our finite difference problem is just set like this. Once we define how we're going to get F, that becomes a grid function. And now the question is, how do we solve this, and what are the characteristics of this finite difference method? And we're going to talk about that next time.